Our next presenter is Mr. Mahdi, who will be presenting his paper on a review of CRC mechanisms and Foss algorithms.
So, good evening. My name is Mahdi Amiri. I work for Sultan Qaboos University in Research Center, and also a master's student. I'm also part of the organization committee for this conference. I should first thank Professor Hadj Bourdoucen and Dr. Afaq Ahmed for their great help and support and giving the opportunity to do this research, learn from them, and write the final report. This report is about a famous redundancy and fault-tolerant algorithm with name of CRC. As you know, error-checking algorithms are mechanisms to make sure data has been transmitted or stored correctly. In other words, they are used for investigating data integrity, which is the common need for today's high-speed communications. Cyclic redundancy check, or simply CRC, is simple, fast, yet powerful common mechanism introduced by Peterson in 1961. CRC is based on the remainder of a polynomial division in the finite field theory and cyclic codes. Since 1961, there are many efforts to improve this mechanism, which notable ones are bitwise, bytewise, various lookup tables, sliced by 4, 8, and recently 16 bytes algorithms. Why we did this research and investigate the CRC mechanism is the fact CRC is used in many communication protocols. Protocols like Ethernet, ISCSI, Bluetooth, ATM, mobile networks, SDLC, HLDC, IRDA, USB, MMC storage are all using CRC mechanism. CRC is also very common in embedded systems. So we can see many different implementations of CRC algorithms with different polynomials, different sizes for check codes, and different methods to add and transmit the data. For instance, there are 4 different algorithms founded in the source code of the Linux kernel about CRC32, which are classic bitwise algorithms, bytewise algorithms, sliced by 4 algorithms, sliced by 8 algorithms. The classic algorithm, which we know it as bitwise algorithm, is originally using numbers of D-type flip-flops to calculate the check bits of CRC. While implementation of the original algorithm is very simple and straightforward in today's computers, it lacks the required speed and will not provide a high throughput result because it is based on bits instead of bytes and boards and double words, which are the most essential calculation units in the computers. A better way to implement the CRC mechanism in computers was to use the previous calculated lookup tables. These tables can be created for either 8-bit or 1 byte or more, like 4, 8, and 16 bytes. Using fast lookup tables for either 4 or 8 bytes simultaneously was introduced by Intel and is merged to the current Linux and FreeBSD kernel source code. Now, a Linux administrator can configure the Linux kernel to support either CRC sliced by 8 algorithm and use 8 bytes simultaneous, which is the default mechanism in Linux kernel and also the BSD, or go for CRC sliced by 4 algorithm and use 4 bytes simultaneously, or select the CRC Sarwat's algorithm, which is 1 byte at the time, or even the classic CRC algorithm, which is 1 bit at a time. The point is Linux is an open source software. And as a Linux system engineer or system administrator, you have the right to choose what is the right algorithm which fits the best for your system architecture. Parts of research, we found the following result from various tests that was done on a general computer with a Core i7 processor. As you can see in the slide, slicing by 8 is almost 16 times faster than the classic CRC algorithm on a general computer, and proposed algorithms by other research for slicing by 16 is even a bit faster than slicing by 8 algorithm, which is already the default algorithm in the Linux kernel. In the conclusion, if you are interested in CRC mechanism, algorithms, coding, and a bit digging inside the Linux kernel, you can read the full paper and keep in touch with us for future works and results. And at the end, I should thank you for participating in this event and listen to this presentation. Any questions are welcome. I will be around.